Hello, I'm Robert, and this time I'm going to talk about whether we can have superflares on the Sun. And the answer is that no, we can't. I'm here from Doomsday Debunked, where we fact check the stories that scare people by looking at what the actual truth is behind the journalism and the scary titles and so on. So first of all, what is a superflare? I'm going to explain why we can't have one. So this is what a superflare is. You've got to distinguish it from coronal mass ejection. They're both explosions that happen in the Sun, and sometimes they happen together, but they're not the same, as this says. So flares are giant bursts of the Sun gets very bright, basically, and it travels at the speed of light, because it just is light. And coronal mass ejection and other forms of energy, X-rays and things. Coronal mass ejections, that is ionizing material. You saw the Earth was there. And they take 1 to 3 days to get to Earth. And they cause the magnetic storms. The solar flares do nothing to us. They're just flashes of light in the Sun. They're nowhere near bright enough to harm us in any way. And the coronal mass ejections, they mainly cause the aurora at the northern and southern poles. So that's a flash. These are the ejection, and that's the solar flare. And then you'll have one with them both together. That's a flare. Coronal mass ejection. And now they're both of them together. You see there's the flare and the ejection as well. That's the ejection. That's the flare. Another ejection, and then both of them together. See, both of them together with it being bright, and then also ejection of material. So that's what a superflare is. That's what a solar flare is. A superflare would be just a very bright flare. And this was a discovery. They found out recently that this was through taking photographs of very distant stars like our Sun in the galaxy. And they found a very small proportion of them suddenly got very bright. And they got so bright that if it had happened happened to our Sun, then the moon rocks would melt. It would be that bright. And the icy moons of Jupiter would have, and the ice would melt there as well, right out to Jupiter. And this hasn't happened in the past, because we can just go and look at these rocks and look at the ice and in the icy moons of Jupiter. They show no signs of having melted. So we obviously haven't had any in the past for billions of years. And then the question was whether it could happen in the future. And when they first discovered this, then for a while there was a possibility that they could have happened in the future. But now we know they can't, because ours is the wrong kind of Sun. And the sort of flare that we do have, the biggest flare they now know that we can have is about 3 times brighter than the Carrington storm. And that was visible in a specialist solar scope, but you wouldn't notice anything without a specialist scope that can look at the Sun in detail. Even the brightest solar flare possible, you wouldn't notice a thing. You only have about as much energy as the Sun outputs in 1/10 of a second. It's not like landscape would get brighter or anything like that. You just wouldn't notice anything. And it couldn't harm us in any way. And so what they found, the reason they know that is partly through observation and statistics, and partly through modelling, which confirms what the statistics say. So the superflare stars, they tend to have a shorter rotation period than our Sun, and they tend to be young. And stars start off rotating very fast, and then they slow down. They start off with stronger magnetic fields and they get weaker. Ours is rotating too slowly, once every 24 days. And its field is too weak. And they also tend to have much larger sunspots, 10% of the Sun, of the star covered or more. Ours are not nearly that big. They're more active than ours. And then the other thing, from modelling, and not direct measurement, but from modelling how a superflare can happen, then they seem to come from stars that have the polar regions rotating faster than equatorial regions. So on our Sun, if the equatorial region is rotating like that, and the polar region is rotating like that very much more slowly. But on these ones, full region rotating like that, the pole region is rotating much faster. And so ours, in all these ways, it's the wrong kind of star to have a superflare. It can still have the ordinary flares, but it can't have a superflare. Now, it can have a coronal mass ejection. So if I just play one of those, and those can be very dramatic, like that. That's actual material from the sun itself going up into space. But by the time it gets to Earth, it's all spread out and it's just a vacuum, and it can't harm us. And it's only the ions in the superflare, not in the coronal mass ejection, that cause magnetic effects on our magnetic field. And those also, then I talk about that separately, but the only effects would be similar to a major solar magnetic storm, at most power cuts for hours, to possibly days, but just in a few places. You're not talking about even taking down the whole of the US grid or something for a day, or even for an hour, because most of the transformers, and they're triply redundant normally, and most of them are designed and they're much stronger nowadays, they're much more resistant to voltage fluctuations, and they wouldn't be knocked out even by a very strong magnetic storm. And they create very weak changes in the magnetic field. They can only make a difference for long power lines that stretch for many kilometers, and they won't do anything to your laptop because your laptop isn't big enough to have any magnetic effects on it from a magnetic storm. And they won't do anything to the optical cables that are used for the internet because they're the wrong kind of material. They only light goes through them, not electricity. So the only thing it can have an effect on is your power grid. And the solar storms, remember I'm now talking about solar storms, I'm not talking about the superflares. Superflares, then they can't do anything. They are just a slight brightening of the sun. That's such a small brightening for our sun that you just won't notice. You just won't notice a thing. And so all we have are these eruptions, and these eruptions of material. Then all they can have are the magnetic effects, and the magnetic effects are way exaggerated by people as well. And as I say, they can't harm your electronic equipment, they can't harm the internet, and they can cause short power cuts, but we're much harder. It's much hardier. It's much more hardened than the Quebec power cut in the 1980s, and that's not going to happen again in the same conditions because we've got better transformers and we've learnt from that. And it would have to be a very strong magnetic field to do anything, and even then just short power cuts. And if you had one of these coronal mass ejection and solar storms, if you had a solar storm, then then the worst effect is it would have some effects on the on satellites and the GPS satellites, and the GPS can glitch during those. There's not really much happens to us, and the particles themselves, they can't get through our atmosphere. The atmosphere blocks all the particles from the sun. The particles that we do get through are from cosmic ray radiation, from much bigger events than can happen on our sun, that happen on other stars and black holes and things, very distant things in our galaxy. And that's what does get through our atmosphere, but it's a kind of constant flux of that, and only small amounts get through. And our bodies are used to them. So there's, my thing's off there. So there's nothing to worry about here.